All right, welcome to Physics 221, Chapter 16. This chapter is about traveling waves. So here are the objectives. We're going to use the wave model and understand how it differs from the particle model. That's very important. And we're going to discuss this again later in the semester. I mean, in Physics 121, most of the time we use a particle model, right? When you were doing force diagrams, you had a car, you do the car as a point, particle. And so now we're doing the wave model, completely different than the particle model. We're going to hopefully visualize wave motion and develop some intuition about waves. We're going to work with functions of two variables because a wave is a function of two variables. Using both graphical and mathematical representations, we'll become familiar with the properties of sine or cosine waves, such as wavelength, wave number, phase, and frequency. Some of you have had this or some of this already. We'll study important characteristics of sound waves and light waves, and then we'll discuss the Doppler effect. The Doppler effect is one of these things where if you hear it the first time, you say, so? But, I mean, we're going to learn a little bit. I mean, this is used in medicine, it's used in weather forecasting. Scientists use the Doppler effect to figure out that the universe is expanding. I mean, it's all over the place in science. So it's very, very important. All right, the wave model. Why do we care about waves? Well, sound is a wave. Light sometimes acts like waves. Quantum mechanics, which we'll study later on, in quantum mechanics, we're going to see that particles, like electrons and protons, sometimes act like waves. Getting back to light, it was Einstein's careful study of light and electricity and magnetism that led him to develop relativity. So waves are incredibly important. I mean, think of sound waves, earthquake waves, seismic waves. Oh, I already said that. All sorts of waves are everywhere. Okay, just to review again. A particle has it's a location in space, right? It's a particle. So what we say it's localized. Now, a wave. Let's see if it's going to work. A wave is really not localized. I mean, with a wave, you can't just say a wave is right there. I mean, a wave is spread out all over the place. So a particle is localized, waves are not localized. Okay, a particle, like a car or a marking pen, has mass. Now, does a wave have mass? I mean, I know the water has mass for a water wave, but does the wave itself, I mean, does that disturbance have mass? No, not at all. How about the ability to pass through something? I mean, if I have two particles colliding, do they pass through each other? Generally not. But what does a wave do? What does a water wave do? So here's a water wave. It just kind of goes around the barber, right? Or how about two water waves? They just go through each other. So this is a nice one. So here we have the particle model. So we have two pitching machines, so they're shooting baseballs. So the balls collide and bounce apart. Two particles cannot occupy the same point of space at the same time. No kidding, right? I mean, right? Okay. Loudspeakers. So they're producing sound waves. The waves pass through each other. The waves pass through each other. So, unlike particles, two waves can pass directly through each other. So, what am I trying to say? What I'm trying to say is particles and waves are completely different. Now you remember that throughout the semester. Particles and waves are completely different. Now, what does this mean? If somebody puts their fingers like this behind their back, what does it mean? It means they're not telling the truth. So remember this, okay? Just remember this slide. All right, there are two types of one-dimensional waves. And there's actually more, but this is, we just want to talk about the regular, periodic, well-defined waves. So I call them physics waves. So there's two types. There's transverse and there's longitudinal. So here's a piece of rope. Let's say it's tied to a doorknob. So let's say, so the doorknob's over there and I have the rope. So I just give it a flick, you know, just like that. So what we're going to notice, so I'm giving it a flick, right, up and down. And so, you know, you're going to see the wave pulse go up, right? I mean, I flicked it up. So you can see the wave pulse go up. But you're going to see that pulse travel towards the doorknob. So that's, what does transverse mean? Transverse means perpendicular. So the displacement, we're going to see that word a lot. The displacement is this way or that way, depends, you know. But the wave motion is going that way, okay? So motion of the wave at speed v that way, the displacement of the rope either that way or that way. So it's perpendicular, so it's transverse wave. Here's a longitudinal wave. So this is a spring, this is just a spring on a table or something, and I'm not going to do this, I'm just going to do this, right? So see how he pushes or pulls, or he or she, whatever, we don't know, right? And so you see the displacement going this way or that way, but you also see the pulse, right? The pulse, the disturbance moved this way. So longitudinal means, you know, like parallel or anti-parallel, whereas this one means perpendicular. That's all. So, you know, rope waves, a sound wave is a longitudinal wave. All right. Now, so what we really care about with waves is the displacement. Okay, the displacement. So that's what we're going to key on. So the displacement of the rope, the displacement of the spring, whatever. So I want to show you a little simulation of a wave. Okay. All right, you see that? So what kind of wave is this? Well, what direction are the pulses moving? The pulses are going this way, right? I mean, look. Okay, let me see if I can get one. All right. So the wave is moving to the right, but yet what's the piece of rope or whatever this crazy thing is doing? Going up and down. So that's a transverse wave, just like a rope, right? Transverse wave. This part goes up and down, but the wave goes transverse or perpendicular to it. Okay, now remember, what we care about is the displacement. So, look at this. What is the displacement of the wave? Now, you should be very confused right now, because in order to answer that question, I have to say, well, when and where, right? I mean, you know, the silly thing is moving. Okay, so all I'm trying to say is that was a not fair question, unfair question. Because in order to say what's the displacement, you have to say where and when, because things are changing. Okay, so you have to say where and when. All right. Oh, I just did that. Okay. All right, so basically the displacement depends on position as well as time. Now, we want to keep things simple for a while. So we're going to consider a sinusoidal wave. Remember learning that term in math? It just means like a sine wave or a cosine wave. Sinusoidal. Now, the thing that's beautiful about this thing is it's periodic. It repeats itself. Okay? Now, it's periodic in wavelength, right? So this is one wavelength. right? The next one's going to be the same thing. It just keeps repeating. So it's periodic in wavelength. So this length is wavelength, right? From here to here is the wavelength. That's a lambda, Greek, you know. All right. So it's periodic in wavelength, and uppercase T is period. So it's the time for one wavelength. Or, like if we were in astronomy, it'd be the time for one complete orbit. If you have a grandfather's clock, it's the time for one cycle. So it starts here, goes there, comes back. So the period is the time. That's why it's a T, right? But it's not any old time. It's a special time. It's the time for one wavelength, time for an orbit, time for a cycle, whatever. So sine and cosine waves are periodic in wavelength and in period. Okay. Question for you. Okay, hold on. Now you're going to look at the graph very, very carefully. So I hope you can see everything on that graph. Okay, so here you have amplitude, right? This is the amplitude. So here's 0. It goes up to here, right? It's like, what's the units? No units. Can't believe it. Whatever. So the amplitude is 1, right? So the amplitude is from the 0 point to this. So the amplitude is 1, and then this is time. So using this graph and no other information, no other equations, no nothing, what is the approximate wavelength of the sine wave? So pause your video and think about it. All right, I hope you've thought about it. Now remember, a wavelength is a length. It's meters. It's not the amplitude. That has nothing to do with it. And this is time. So how in the world can you get a wavelength from a time graph? You can't. So that was the whole point of this question. Again, I'm being totally unfair. So none of the above, okay? Because it's time, all right? So you can't get a wavelength from time. So that was rotten. Okay, so here's another question. Oops. All right. Now we have an amplitude again, which is meters. And now we have time. So now the question is, what is the approximate period of the sine wave? In other words, how long does it take for one wavelength to, what's the time for one wavelength, or one cycle, one orbit? Well, now I can just do it, right? So this is 0 time. This is, I don't know. Well, it's like, I don't know. What do you think? 9.5 or something like that? Well, let's put it this way. It's not, okay, 1 meter is ridiculous because period is time. 6.2 meters is ridiculous. 6.2 seconds, that would be like right here. That's ridiculous. So it looks like it's like 9.5 seconds, right? Here's 9, you know, somewhere there. Ah, come on. Okay, so that's the period. The period is a time for one complete wavelength. So it's about, what? Wait a second. Was I crazy on that last one? Yeah, I was crazy. I'm sorry. I don't know what I was thinking. This is one wavelength here. Sorry. From here, right? From here to here is one wavelength. So it is 6.2. Sorry, Monday morning, you know, what can I say? All right, so the period is the time for one wavelength, 6.2, not 9.5. Okay, one more question. Okay, now I'll do this one right. What's the approximate wavelength? So look at it and figure it out. All right, so here's one wavelength, right? So that's, I don't know, 6 or something. Okay, it's not 3 centimeters, because that'd be here, that's a half. It's 6. It's not 6 seconds, because it's wavelength, meters, or whatever, centimeters. All right, so that's the wavelength. That's the wavelength, right? This distance, this distance. Okay, wonderful. Now, so what have we seen? You know, we know that the wave is periodic in space and time, wavelength and period. So how many graphs do we really need to visualize a wave? You need two. You need one with time on the x-axis and the other with distance on the x-axis. So if you read the textbook, Randy Knight calls them history graphs and snapshot graphs. Randy Knight goes into a gory detail, which I'm not going to because I don't think it's worth the trouble, to tell you the truth. All right, so there you go. But you can disagree and read it and study it. That's okay. Okay, so this is a sine wave, and we have time on the horizontal axis. So does this give us the history of the displacement, or is it a snapshot? Okay, think about a snapshot. What is a snapshot? Well, you know, when you take a picture of something with a camera, you call that taking a snapshot. So you're looking at whatever you're taking a picture of at that one particular time. But here, though, here we see the displacement throughout, well, from 0 to 10 seconds. So we're seeing the history of the displacement. So obviously, this is a history graph, right? This is a history graph. All right? Now, here's the important thing. A history graph shows the position of a single piece of the wave at one, you know, for a given amount of time. Yeah, okay. All right? So what I'm saying is, let me back off. Let's say we have a rope tied to the doorknob. Let's say I take a can of spray paint, and I spray just one piece of that rope. And then I start making these transverse waves. Okay? So the history graph shows what happens to that one spot of the rope that I painted for however long you care to take data, right? So it's the history of one piece of the rope. That's it. On the other hand, here, look at, there's no time, right? There's no time. And we just see, you know, we see distance. So this is called a snapshot. This is what, again, just pretend I have a rope and I'm doing my little thing here. And this is what the rope looks like at one particular time, right? Because there's no time. So it's one particular time. This is the entire rope for one particular time. So that's the snapshot, right? That's the snapshot. Okay? And again, we need this plot, the snapshot, as well as this plot to really understand what's going on, because the displacement depends on the position as well as the time. Okay. All right, let's switch. Now let's see a little simulation again. Okay, let's just, same thing as we saw before. All right. So back to our transverse wave. Okay, now what is being transported between this piece of the rope and this piece of the rope? What's being transported? I mean, is there actually a piece of rope that's moving from here to here? Well, that's a ridiculous question. Of course not, right? I mean, this piece of rope stays there, right? This piece of rope, well, I mean, this piece of rope goes like that, but I mean, it doesn't move over there. You know, this piece of rope, the very end of this rope, is going up and down. So there's not a piece of rope that moves from here to there, okay? All right, so, therefore, what is moving from here to here? I mean, come on. Something's actually moving. We can see it, right? You know? So what is it that's moving? It's called a disturbance. A disturbance. Now, is a disturbance a piece of rope? No. Does a disturbance have mass? No. All right? Okay, now what I want you to do, I want you to concentrate on this second, okay, this is the first green section, this is the second green section, right? So focus, maybe I'll slow it down, yeah. Slow motion, okay. All right, so focus on this piece right there, that second green one, all right? So what's going on? What is it doing? Well, you already know what it's doing. We already talked about it. This, just like everything else, it's just going up and down, right? Just going up and down, up and up, up and down, okay? So this is an actual piece of the rope, correct? And this actual piece of the rope is going up and down. The disturbance is going this way, but the actual piece of the rope, you know, that I sprayed with my can of spray paint, is just going up and down. I mean, that's what a transverse wave is, okay? All right. Okay, back to this picture. So, I mean, you're all familiar with this, right? Let's just say that the water wave goes this way. But what does the fishing bobber do? Does the fishing bobber go this way as well? Well, no. It just goes up and down, up and down, up and down, up and down, right? I mean, that's why you use a fishing bobber, to keep the hook and the bait at the same place. Okay, now, okay, so let's say you're holding the end of the rope or you're holding the end of the spring. Now, if you know, and let's say for this one, you know, I'm going like that. For this one, I'm going like that. What would you feel? What would you feel if you were holding the end? Well, you'd feel vibrations, obviously. Now, work is required to produce these vibrations, right? And work requires energy. So, what is being transported by the wave? Energy, right? Energy. And also, we'll talk about later, momentum. Think about light waves. Do light waves transport energy? Well, let's see. Think about it. I mean, have you ever got a sunburn? Where did the energy come to burn your sun? I mean, can't believe I said that. Where did the energy come to burn your skin? The sun, right? Well, gee, that's 93 million miles away. How'd it get here? With a wave, a light wave. Okay? All right. So, what is a good definition of a wave? So here's a nice definition of a wave. A wave is a self-propagating disturbance that travels through an elastic medium and transports energy and momentum. All right, what's the self-propagating bit? Well, you know, like a rope, right? I just have to shake it a couple times and it's just going to keep on going, you know. Elastic medium. Okay, I wanted to put quotes around the word elastic. I mean, think of a seismic wave. Seismic waves going through the earth. Do you typically think of the earth as being elastic? Well, yeah, it moves, right? So, I mean, it really is elastic, okay? So, all right. Okay, so self-propagating disturbance, elastic medium, transports energy. So what's the medium for a sound wave? Air. So if you went to the moon, could you hear each other talk? No. What's the medium for a rope wave? That's a dumb question, huh? Rope. What's the medium for a water wave? Water. What's the medium for a seismic wave? Earth, and so forth and so on. It's not all that easy, though. You wait. All right. Okay, so here's a question. Come on. What's your problem? All right, so pause your video and figure this out. Well, I'll read it. Okay, a wave is sent along a long spring, so we're talking about longitudinal wave, right? So a longitudinal wave is sent along a long spring by moving this left end rapidly to the right, so just to the right, and keeping it there. So the figure shows the wave pulse at, see, you can see the little, it's kind of compressed there. So that's the wave pulse. So the figure shows the wave pulse at QR. So part RS of the wave is yet undisturbed. Which of the graphs, 1 through 5, correctly shows the relation between the displacement S, which is like delta x, right? The displacement S is like delta x, where this is x. So which graph shows the relation between the displacement S and the position x? The displacements to the right are positive. Okay, so pause your video and figure this out. Don't cheat. Okay, so it's this one, right? Because look at what happened to P. It moved over here. What happened to this spot? It moved over to here, right? So all these things move over. But then here, they don't move over. And so see everything here? So this part here is that. So everything here moved over by a certain amount. So this is 0 displacement. This is delta x, or S. So all of these guys, every one of these pieces of spring moved over the same amount. Okay? All right. How are we doing on time, Sully? No, I mean for this one, for this.
Doing good. We've got 2 hours left.
No, but I mean, how long is this one?
This one's quite a bit. This one's about 40 minutes.
Oh, let's stop.